Hello, calculus students. In this video, we are going to talk about our 7.2a notes. It's called the disc and washer method, and what that means is we're going to use a method called the disc and washer method to find the volume of some three-dimensional shapes. So in our last lesson, we learned how to use your new calculus skills to find the areas of some shapes that were some unusual shapes. They were shapes that would not have lended themselves to the formulas from geometry that you already knew. So we had to use calculus to find those areas. So what we're going to do in this lesson is we're going to step into three-dimensional space, and we're going to talk about how to find volumes of some unusual shapes using methods called the disc and washer method. So the first thing we need to talk about is what a solid of revolution is. And that is formed when a region in a plane is revolved around a line, and that line is called the axis of revolution. So for example, let's take this rectangle. Now this rectangle has a height of, we're going to call it capital R, and we'll see why we're choosing capital R in just a minute. But it has a height of capital R and a width of W. Now if we were to take that rectangle and we were to revolve it around an axis, that axis again is called the axis of revolution. Taking that shape and revolving it around an axis would result in this shape. Sometimes we call this shape a disc, hence the disc method. But what this actually is a shape that you're familiar with from your geometry courses. And we have what's called a right cylinder is what it is. So we take this rectangle, we rotate it around an axis, and it carves out in 3D space. It's going to carve out this this right cylinder. Okay, so let's talk about how to find the volume of a right cylinder. Well, that's something you know from your geometry courses. To find the volume of a right cylinder, we'll take the area of its base times its height. Okay, so in this case, its base would be a circle. And how do we find the area of a circle? We find the area of a circle by taking pi times the radius squared. So you'll notice in our picture that the radius of our circle, here let me draw the radius from the center. The radius of our circle is, we're going to call it capital R. So if we take pi times capital R squared, that's the area of the base. Okay, that's what the capital B stood for. And then the height of this cylinder, well, a height of a cylinder would be the distance from one base to another. So in this picture, you can see that the distance from one base to another is given as W. So pi R squared W would be the area, or excuse me, not the area, but that would give you the volume of this disc or this right cylinder that was formed when we took a rectangle and we rotated it about an axis. So now let's take a look at a more unusual shape rather than a rectangle. Let's take a look at this region right here that's formed by a function. It has a left bound and a right bound. And what we've talked about so far is how to find the area of this region. And we can find the area of the region by taking an integral. Remember how we defined integrals. If we took, here's one representative rectangle whose width would be delta x and whose height would be whatever this function value is. Now if we were to fill up this entire region with rectangles whose heights are, whose widths are delta x and whose heights are r, which would be this function value. And then if we increase the number of those rectangles, in fact, we could increase the number of rectangles on into infinity, then the sum of the areas of those rectangles would start to approximate the area of this region. Well, we're going to do that same idea to find volume, except what we're going to do is we're going to take this unusual shaped region and we're going to rotate it about an axis. So if we were to take that shape and rotate it about an axis, we would have this blue shape. It kind of looks like a toilet bowl plunger for a better description of it. But we can find the volume of this shape, this three-dimensional shape, by looking at the sum of the volumes of a bunch of discs or a bunch of right cylinders. So in other words, if I were to take one of this one representative rectangle and rotate it about an axis, we would have this disk. Now we know how to find the area, or excuse me, the volume of this disk. We would take pi r squared times its height, which would be delta x. That would be the volume of one disk. So imagine if we take several disks, okay? Let's just back up and remind us that the volume of this one representative disk would be, its volume would be pi times capital R squared, that's the area of the base, and then times delta x would be the distance from one base to another, so that would be the height of that cylinder. So that would be how to find the area of one of those disks. So imagine finding the area of all of these disks, and you can see that if we were to add all those volumes together, it would start to approximate the area of this blue three-dimensional shape. Well, so let's think of it this way. If we were to add up the volumes of all of those disks, then we could take a sum as, let's pick I for a counter, as I goes from 1 to n of, now I'm going to put pi out in front because every one of these would have a factor of pi. Let's put pi out in front and then multiply that by capital R of x sub I, which would be the height, or excuse me, would be the radius of each rectangle. So pi times the radius of each rectangle squared would be the area of each base. And then if we multiply that by delta x, that would be the height of a disk. So all that to say, this is just a fancy way of saying if you add up the volumes of all these disks, we're getting closer and closer to the volume of this shape, okay? Now, let's go ahead and simplify this a little bit. I'm going to pull that pi out in front of the sigma sign. That would be the same thing as pi times the sum as I goes from 1 to infinity, or not 1 to infinity, 1 to n of R of x sub I. Now that would give me the radius of each disk, and then multiply it by the height of each of those cylinders or disks, delta x. And all I did is I just pulled the pi out in front. Now that would be the sum of n rectangles. So now imagine, if you will, if we were to take a limit as n approaches infinity, let's let the number of disks, or the number of right cylinders, just increase on into infinity. So if we take the limit as n approaches infinity of pi times the sum as I goes from 1 to n of R of x sub I squared, so pi r squared, and then times the height of each one, what that is an integral, isn't it? It's the definition of an integral. So we could rewrite this as pi times the integral from a to b. Remember, those bounds come from here. The left bound was a and the right bound was b. So the integral from a to b of r of x squared, that would be the radius of any one of those disks, and then times the change in x, which we're just going to call delta x. So all that fancy stuff to say, this is how we can find the volume of a shape that's some unusual shape that we couldn't use a formula from geometry to find. So this fancy formula is what we call the disk method. So let's just write down what it is. It is the disk method. And what is it the disk method of? It's the disk method of finding, see if I can squeeze this in here, finding the volume of a solid. So one more time, if we were to take a solid and we rotate it about a horizontal axis of revolution, like is happening here, so we have this shape, we're going to rotate it about a horizontal axis. What that leads us to do is we're going to integrate with respect to x. So we integrate with respect to x if we are rotating our shape about a horizontal axis. And so the formula for finding the volume is given right here again. It's pi times the integral from a to b of r of x squared, where r of x is the height of every one of those rectangles, or after they're rotated, it would be the radius of every one of the discs, and then times dx, which is your change in x, delta x. That would be the height of each one of those discs. Now, we can also take a shape and we can rotate it about a vertical axis of revolution. So I suppose you can probably guess that if we're going to rotate it about a vertical axis of revolution, that means instead of integrating with respect to x, then this time we would integrate with respect to y. So integrate with respect to y. So if that's the case, then here's our formula. It's kind of tiny, but there's our formula to find the volume of a shape that would happen when we take a region and we rotate it about a vertical axis of revolution. So it would be pi times the integral from c to d. Now, if we are integrating with respect to y, we would need y bounds, so from bottom to top, c to d, of r of y squared, where r of y is the radius of one of those discs. Remember, in 2 dimensions, this is a rectangle, but if I were to take that rectangle and rotate it about an axis, we'd have a disc, and the radius of that disc would be r of y squared, and then times dy. dy is your delta y, your change in y, which would be the height of each one of those discs. So let's take a look at some examples and see how this works. So example number 1 says, find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of x, or excuse me, the square root of sine x, that's this function right here, and the x-axis from 0 to pi, and we're going to take that shape and we're going to rotate it about the x-axis. Okay, so to find the volume, first of all, since we're rotating about the x-axis, then let's start by writing our formula. That would be v equals pi times the integral from a to b of r of x, that would be the radius of each of those discs squared, times delta x, the change in x. So in this case, this is going to be pi times the integral of, now since we're integrating with respect to x, we need x bounds, so our bounds go from 0 to pi. So we're going to integrate from 0 to pi of r of x. Well, r of x is a function value, isn't it? R of x is the function value. It's the output when we put x into this function. So let's just make a note here. R of x is the square root of sine x. All right, so we're going to take the square root of sine x, that is our r of x, and then what do we do with r of x? We square it, so put an exponent of 2, and then don't forget your dx. All right, so we can simplify this a little bit because you'll notice we have a square root that's being squared, and squaring and square roots are inverses of each other. So we can simplify this and rewrite it as pi times the integral from 0 to pi of just sine x dx, all right? And so now we can find the antiderivative and then find the actual area. So this is going to be pi times the antiderivative of sine x is negative cosine x, and then we're going to evaluate that from 0 to pi. So this would be pi times, let's start some parentheses, and let's first replace x with pi. So this would be negative cosine pi, and then minus cosine 0, okay? And we can simplify that a little bit. Let's see, cosine of pi, that would be here on the unit circle, where the x value is negative 1. So we're going to take the opposite of cosine of pi, that would be the opposite of negative 1, which is just 1, and then minus the cosine of 0. Remember, cosine of 0 is here on the unit circle, where the x value is positive 1. So, and you may have noticed that I dropped a negative sign right here, didn't I? Because we replaced x with pi, so that would be negative cosine pi minus, this should be negative cosine 0. So let me put a negative in there. And then, of course, subtracting a negative is the same thing as adding a positive. So we're actually going to add the cosine of 0, and remember cosine of 0 is positive 1, and so we get 1 plus 1 times pi, which is 2 pi. All right, so what did we just find? What were we asked to find? We were asked to find the volume of a three-dimensional shape that happens when we take this region and we rotate it about the x-axis. So when we take this region and rotate it about the x-axis, we get this football kind of shaped thing. This is not a shape that you know any geometry formula for to find the volume. So we had to use calculus, and our final answer then is 2 pi, and that would be in some kind of units cubed. Then in example number 2, this one says, find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. So this is a slightly different from the last one in that we're not going to rotate a region about the x-axis. We're going to rotate it about a different horizontal line, and that is the line y equals 1. Okay, so a good place to start is the formula for finding the volume of a solid that's formed by rotating a region about a horizontal axis. So that formula looks like this. It's capital V for volume is equal to pi times the integral from a to b of r of x, that would be the radius of each one of those discs, squared times the change in x, delta x. Okay, so let's go ahead. I guess we can start by filling in our bounds. Our bounds go from A to B. So if you look at our graph, our left bound is -1 and the right bound is +1. So we're going to integrate from -1 to +1. And now let's talk about this r of x. Okay, remember r of x would be the height of this representative rectangle, or after the rotation, it would be the radius of a right cylinder, or the radius of a disc. So let's talk about how we would find r of x. Well, r of x, let's do it over here. Capital R of x, if you look at our picture, notice that r of x would be what we get when we take this function value, f of x, and we subtract g of x. So r of x is equal to f of x minus g of x, all right? And then let's fill in our function values. F of x, we're told, is 2 minus x squared, and g of x is equal to 1. So that would be 2 minus x squared minus 1, or we can simplify that and call that 1 minus x squared. So that's our r of x that's going to go right here. So we will take 1 minus x squared, 1 minus x squared, and then we're going to square that. And then don't forget about your dx. Okay, so now, before we find the antiderivative, let's go ahead and take this binomial and square it. Then we can integrate term by term. So we would have pi times the integral from -1 to 1. When you square a binomial, you should get a trinomial. The first term would be 1 squared, and then the second term would be what you get when you multiply these two terms together and double that result. So that would be -2x squared, and then plus the last term is the second term squared, and x squared squared would be x to the fourth. X to the fourth. And then don't forget about your dx. So now we can find the antiderivative term by term. So we'll take pi times the integral from -1 to 1 of x minus, let's see, the antiderivative of 2x squared would be 2x to the third over 3. So that's 2x to the third over 3, and then plus x to the fifth over 5, which is the antiderivative of x to the fourth. All right. Oops. Why do I still have a, sorry about that. Why do I still have an integral and a dx sign? Let me fix that because we were just integrating. So let me get rid of this, and let me get rid of this. I'm so sorry about this, guys. So this should be pi times this expression that we're going to evaluate from -1 to 1. All right, so let's start doing that. So we're going to first of all, replace all the x's with 1. So that would be 1 minus 2 times 1 cubed is just 2. So minus 2/3, and then plus 1/5, because 1 to the 5th is 5. And then minus, now we need to go back and we need to replace all these x's. Now we need to replace them with -1. So that would be -1. And then remember, -1 cubed is -1 times -1 times -1, which is -1, which we multiply by this -2. So that will change this to plus 2/3. And then minus 1/5, because -1 to the 5th would be 5. Okay, so now we just have a bunch of arithmetic to do. I'm not going to take time in this video to do that. I can let you do that on your own, but when you're all done, your answer should be 16 pi over 15. Okay, so what did we just do? We used our formula to find the volume of a solid that is that occurs when you take a region and rotate it about a horizontal axis. And when we do that, we would get this shape. Okay, it's been rotated about this line, y equals 1, and the volume of that shape then would be 16 pi over 15, some kind of units cubed. So now let's take a look at the washer method for finding the volume of a solid that occurs when you rotate a region about an axis. So when do we use the washer method? Well, if the solid of revolution has a hole or some empty space, that's when we extend the idea of a disc to the idea of a washer. So first of all, I need you to know what a washer is. A washer is just a right cylinder or a disc that has a hole in the middle of it. So let me attempt to draw. A washer would look something like this. Okay, so a right cylinder that has a hole in the middle. Okay, so suppose we took a rectangle, and this rectangle has a height of, actually it would be a height of capital R minus little r, and a width of W. If we were to take that rectangle and rotate it about an axis, well, it would carve out this shape. It would carve out this washer shape. It would almost look like a disc, except there would be this empty space in the middle because of this empty space right here. All right? So now, how would we find the volume of this right cylinder or this disc that has a hole in it? Well, you probably remember doing these kind of problems in geometry. To find the volume, what we're going to do is we're going to take the volume of the outer cylinder, and then we're going to subtract that empty inner cylinder. Okay, so wait, that's not done. Hold on, that doesn't spell cylinder. Let me fix that. The inner cylinder, which is that empty space. Cylinder. There we go. Okay, so how do we find the volume of the outer cylinder? Well, the outer cylinder is a cylinder. We would take the area of its base, which would be pi times capital R squared, and then we multiply it by its height. And remember, the height of the cylinder is the distance from one base to another, which we're going to call W in this diagram. So we're going to take pi times capital R squared times W. That's the area of the base of this outer cylinder times the height of that outer cylinder. And then we're going to subtract from that the volume of the inner cylinder, which would be pi times, well, this inner cylinder has a radius of little r. So that would be little r squared, and then times W. It would have the same height as the outer cylinder. And then we can simplify this a little bit. We can pull the pi out, and we'd have pi times capital R squared minus little r squared, and then we're going to pull the W out as well, but we're going to put that on the right side. So in other words, to find the volume of a washer, we're going to take pi times the integral from A to B of the outer radius, which is capital R of X, and we're going to take that outer radius and square it, minus the inner radius, which would be little r of X squared, And then the W would be our delta x, our change in x. And then why don't we do this? We can even put some parentheses around this whole thing so we know what our integrand is. So let's use the washer method to work this next problem. It says, find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x. This is y equals the square root of x. And let me slide this over just a little bit. And the graph of y equals, y equals x squared, which is this function. Okay, now, if we were to take that region bounded by y equals square root of x and y equals x squared from 0 to 1, because those are their points of intersection, if we were to take that and rotate it about an axis, a horizontal axis, we would get this shape. Okay, so here was our original shape. Okay, it got rotated around the axis. So I hope you can tell from this picture, I don't know how clear it is on your notes, that there's some empty space in here, isn't there? So if we look, so we could approximate the volume of this solid by looking at the volumes of a whole bunch of washers. So let's take, for example, this representative rectangle. If we were to take that rectangle and rotate it about the x-axis, you wouldn't have a solid disk this time. You would have a washer. Because of this empty space, there would be a hole in the middle. So if you can think of an infinite number of those washers and their volumes all being added together, that's what this volume formula represents. Let's go ahead and write the formula. It is equal to pi times the integral from a to b of, let's start some brackets, of r of x, that outer radius squared, minus little r of x, that inner radius squared, close off your brackets, and dx. All right, so let's fill in for this problem. So it would be pi times the integral, well, from a to b. So what are our bounds? Now we're integrating with respect to x, so we need x bounds. They would go from 0 to 1. Okay, so the integral from 0 to 1 of, now, what is the outer radius? So the outer radius would be this capital R, okay, which would be these function values, which would be the square root of x, okay? So this y equals the square root of x is how we get our outer radius. So we're going to take the square root of x squared and then minus the inner radius. Well, the inner radius is these function values. And how do we get these function values? We use y equals x squared. So our little r is just x squared. So we're going to take x squared, and we're going to square that. Close the brackets, and don't forget your dx. Okay, so let's simplify a little bit before we take the find the antiderivative. This would be pi times the integral from 0 to 1 of, when we take the square root of x and square it, we would just get x. So that would be x minus, and then x squared to squared. Remember, when you have a power raised to a power, you multiply those exponents. So that would be x to the 4th, and then dx. All right, so now let's find the antiderivative. So this would be pi times x squared over 2 minus x to the 5th over 5, evaluated from 0 to 1. And then to keep this video from getting too long, I'm going to go ahead and tell you the answer. We've done enough of these. I think you could work it out on your own. But the volume turns out to be 3 times pi over 10. And that's the volume of this region that occurred when we took this, this shape, this three-dimensional shape, that happens when we take this region, rotate it about a horizontal axis, and it has this empty space inside. And now let's take a look at one more example, because I want you to see one where we have a solid that's formed when we take a shape like this shape, only this time we're going to rotate it about the y-axis instead of rotating it about the x-axis. So that means we're going to have to integrate with respect to y. So the problem says, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, that's this, y equals 0, which is our x-axis, x equals 0, which is the y-axis, and then this vertical line x equals 1. So we're going to take that region, we're going to rotate it about the y-axis, and when we do, we get this shape, okay? So since we've rotated about the y-axis, we're going to have to integrate with respect to y. And so as we look at this shape from bottom to top, we're going to actually break it up into two shapes, okay? There's this bottom cylinder, if you will. Let me see if I can kind of draw it over here so it would look something like this. This bottom cylinder, okay, that's formed when we take this rectangular region and rotate it around the x-axis. And then the upper part of our shape happens when we take this and rotate it around the y-axis, and it looks kind of like a bowl, sort of. It's got this bowl shape on the inside that's empty, and then all this air volume on the outside. So we're actually going to break this up into pieces, and we're going to do some calculus that's really not necessary, because we could actually find the volume, this cylinder, this bottom part of the solid, we could find it using a geometry formula for the volume of a cylinder, but we're going to go ahead and use calculus to find that volume to practice. So let's start with talking about this bottom part. So to find the volume, we're going to take pi times the integral of, now since we're going to be integrating with respect to y, we need y bounds. So think of those y bounds going from bottom to top. So we're going to go from 0 to 1 of this outer radius. Now it's going to be a horizontal radius this time, since we are integrating with respect to y. In other words, if I were to take this rectangle and rotate it about the y-axis, I'd have a disc. But we're going to go ahead and use the washer formula. Again, it's not necessary. We could have used the disc formula. But we're going to take this outer radius, which is capital R, which is 1. So the outer radius squared minus the inner radius. Well, the inner radius would be 0, wouldn't it? Okay, there is no inner radius. There's no empty space here. So minus 0 squared, and then dy. Now, all of this could have been done using geometry, couldn't it? Okay, so this really is some unnecessary calculus, but I wanted to do it anyway just to practice. So that would give us the volume of this bottom part of the shape. Now, to get the volume of the upper part, we're going to add to that, let's see, we're going to add to that pi times the integral of and then we need some y bounds going from 1 to 2 now. So those y bounds go from 1 to 2 of the outer radius squared. Well, that outer radius, that capital R, from here to here, or from here to here would be 1. I guess there's a good place to see capital R. So the outer radius is 1. So that's going to be 1 squared, and then minus the inner radius. And the inner radius we find by using this function, which is the square root of y minus 1. I guess we should have taken a minute to do that. If let's take a look up here. If y equals x squared plus 1, we need to solve this for x if we're going to be integrating with respect to y. So that would be, let's see, y minus 1 equals x squared, and then we take the square root of both sides, so x equals the square root of y minus 1. So that's the function that we'll use to get our inner radius. So we'll take that little r, which is the square root of y minus 1, and we'll square that. So the square root of y minus 1, the whole thing squared, and then don't forget your dy. So this entire expression is what we would use to find the volume of this solid. Let's go ahead and just simplify a little bit more. We may not finish this problem completely. But this first integral we could rewrite as pi times the integral from 0 to 1 of just 1 dy, and then plus pi times the integral from 1 to 2 of, now if we take the square root of y minus 1 and square that, this square and this square root will cancel out each other, and then we can simplify. 1 minus a negative 1 would be 2, so we can just call that integrand 2 minus y, dy. And then let's just go ahead and take one more step and find the antiderivative. So this would be pi times the antiderivative of 1 with respect to y would just be y, evaluating from 0 to 1. And then plus pi times the antiderivative of 2 minus y would be 2y minus y squared over 2. And that would be evaluated from 1 to 2. Okay, so I think we'll stop there because you could take it from here to finish this problem. On the last page of your notes are some problems that we will be working on in class, but you might want to go ahead and get started on them just so you don't forget what you've worked on in these notes. And then we'll finish it up in class and clear up any questions, and you'll get an opportunity to get a lot of help. So I will see you in class. Oops. What just happened? Let me fix that. Oh, I went to the next.